Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Last classes we have just started our discussion on introduction to high temperature materials. Today we will continue that discussion. In the last class we have talked about what are the main and important characteristic a high temperature material should exhibit, or engineers before design and application of a material at higher temperature, what are the characteristics they really look for. However, a material may satisfy our criteria or may not, but if a material can satisfy our criteria, can we increase the capability of that material to a much better condition? That is one of the question. Whether we can use our engineering and science knowledge and changes or bring changes into the material so that they could serve our purpose in a better way, or a better service life could be expected from a material. In that case, we have to learn some of the very important aspects of metallurgy. Today, we will discuss those things, means how to enhance the capability of a high temperature material for a better service. Since we mostly talked about metals and alloys, there are some of the mechanisms that play a very crucial role on their capability for using at higher temperature. So, here I have just listed those particular mechanism that plays on enhancing the strength and for their other mechanical or aspects, like solid solution strengthening. Okay? Because solid solution strengthening means we add a solid atom in order to increase the lattice friction, as well as it simply stop some of this dislocation, and the friction stresses also increases. Now, in case of precipitation hardening, the precipitate act as a obstacle for dislocation movement and increases the strength. Okay. Dispersion hardening, where precipitate get dissolved at higher temperature, dispersion strengthening is done using some second phase oxide or nitride or some ceramic particle in a metal matrix. Now, there could be effect from the grain size and grain boundary and environmental resistance. So, in other class of material there are some other important aspect like ceramic material, which is also used for higher temperature application, where the volume fraction of different phases, where defect tolerance has to be considered, or let us say thermal shock resistance. Now, in case of composite material, like I have a metal matrix and we incorporate some other second phase ceramic fiber or particle in order to exploit those material for higher temperature, and there we have a small window of enhancing the capabilities in terms of their strength, okay, by controlling the volume fraction of the second phase and so on, or let us say the stiffness, whether we can enhance those property or not, and that is why I write here as a enhanced capability. Okay, means it has already some capability, however, we want to enhance the capability for a better service life. Now, in case of carbon-carbon composite, usually people or engineers look for a better defect tolerance and to get a reliability of the processing and application, whether we can use the stiffness, and since the material contain carbon, once it is exposed to a relatively higher temperature, carbon for carbon dioxide is volatile in nature. So, immediately there is a degradation occur, you understand the matter now. So, the oxidation aggravates, Now, in case of ceramic matrix, again the same question comes, the defect tolerance. Okay. So, this is a very common aspect for any kind of ceramic material, for defect tolerance. Why? Because a ceramic has a lower fracture toughness. I discussed in the very initial days, like K1C. Okay. So, here if the fracture toughness is very low, then if it contain very small crack, that can directly cause to a failure. Okay. The critical crack length size is very small, in the range of a few micrometer, and also the stress redistribution also decreases. So, also we need some reliability. So, we will discuss these aspects today in detail. Let us first start with the metallic alloys in terms of solid solution strengthening. And if we add a solute atom, it causes strengthening. There is no doubt, this is from a very basic understanding of metallurgy, physical metallurgy, that we have learned. However, the internal strain here plays the crucial role in the parent lattice due to the presence of the solute atom that causes the strengthening. However, the atoms with similar crystal structure and very close lattice parameter exhibit higher mutual solubility. Okay. Like I can simply think about copper and nickel. Okay. However, they will generate a relatively smaller strengthening effect, okay, because they have the same crystal structure and the lattice parameter difference is less, okay, and that will cause a lesser strain, internal strain in the material. So, atoms with larger difference in their size will have limited solubility, but it could generate a significant strengthening effect. Okay. So, one has to choose which solute atom we really incorporate, up to what extent, means I am talking about concentration, to generate how much increment in the strength. So, let us say here I talk about let us say the change of the strength. Okay. So, this is not the absolute value of the proof stress or yield strength in a gamma iron. However, we are talking about the delta sigma. Okay. So, this is the percentage or atomic percentage of the alloying element. If we add vanadium, then there will be slight rise. Okay. However, if we add nitrogen, you see it has a very sharp rise. So, this is just an example that I like to show you, that how the solute atom can changes the yield strength depending on the concentration and their relative size difference. Now, in case of nickel based superalloy, it is very common to add tungsten and molybdenum. So, tungsten and molybdenums are added purposely in order to enhance the strengthening by solid solution strengthening. However, these days rhenium is also is added, which has some different effect, not only solid solution strengthening, but also it decreases the diffusivity and also it retards the coarsening effect. Okay. So, if you have precipitate, if you have grains, they may coarsen. Okay. So, in that case, if we can simply stop this coarsening, then we can exploit the coarsening effect of, let us say, the precipitate, which is gamma prime nickel 3 aluminum phase in a gamma nickel matrix in the nickel based superalloys. So, you can see that the very basic engineering comes from the alloy addition and how the alloy addition can changes the relative strength in a lattice. Now, the second issue is the precipitation strengthening. So, by precipitation strengthening, we can enhance the strength of an alloy. How we do that? It is very common age old strategy, like we dissolve a second phase in a matrix by heating above the solvus. How we should see the phase diagram, and here I show you a nickel and aluminum phase diagram. Okay. So, this is the solvus line. Okay. So, here is the gamma phase is stable and here is the gamma and gamma phase is stable. let us assume that I have chosen a composition, here it is C0, and now I simply raise the temperature to a gamma phase field. In that case, I will have grains with gamma only. This is the grain boundaries of gamma. Okay. Now, this is called solution treatment, means I reach to a single solid solution phase where we are holding it without allowing too much grain growth. Okay. And in order to homogenize and dissolve the precipitate which appears initially, after that we simply quench it to a room temperature. Okay. And after quenching, what we get by this rapid quenching from the solution treatment, we get a super saturated solid solution. Okay. This is called super saturated solid solution. Here also we get gamma, however, it contain a higher amount of aluminum, or the net amount of aluminum, all aluminum is inside this gamma solid solution, okay, which is higher than the equilibrium condition. Now, what we do, we basically reform the phase, means the gamma prime phase should again appear by heating at a temperature below the solvers. So, we take again this C0 and we simply warm it up to different temperature for different time for precipitate to appear in the microstructure. And if we heat it at a relatively higher temperature very close to the solvers, then we will get a larger size gamma prime phase, whereas if we heat it to a relatively lower temperature, then we will get more finer precipitate, okay, and more finer, more number. Okay. And because if we have a lower, then the nucleation will be higher and higher and the diffusivity will be less. So, there will be very close particles close to each other, but at higher temperature, since diffusive length is higher and higher. So, we will get a relatively less number of nuclei and a coarser microstructure, means coarser precipitate. Okay. Now, this is, we call it somewhat like a over edged, or this is, let us say, what we really desired as a precipitation treatment that is necessary. Why? Because the size of this precipitate has some role on the mechanism, because it controls the mechanism of strengthening. How? This precipitate actually impede the dislocation movement. The main reason of this precipitate, when the dislocation will appear, it will create as a obstacle. So, for that particular purpose, the dislocation may bypass by climbing, or it may leave a loop around the particles, or it can cut through. How does it occur? I have a particle here, I have the dislocation which is trying to pass, and this is the precipitate. Okay. The dislocation may leave a loop and then dislocation comes here, or it can simply cut through the precipitate. So, this is, let us say, the precipitate, and then after cutting it will be something like this, and here is the dislocation. Okay. So, this is like the situation. So, we can think about which one is better in terms of controlling the mechanism. So, we will see that how to alter and how to control such a circumstance and situation. So, in case of precipitation strengthening, we have seen that if the precipitate diameter is very large, then it basically bypass, or it will climb the dislocation. This is a dislocation climb action, or dislocation will cut through the precipitate when the precipitate is smaller in size. So, this strengthening actually depends on the compatibility between the precipitate and the matrix in terms of their crystal structure, because the parent crystal structure may be different than the precipitate crystal structure, or they may be both are, let us say, FCC phase. However, the lattice parameter may be changed, because if lattice parameter change, then the question of coherency of the precipitate or non-coherency or incoherent or semi-coherent type of precipitate may appear. Okay. And also there are volume fraction of the precipitate that control, or the size of the precipitate. Here I just show you in terms of their size. However, one has to consider all these aspects in terms of crystal structure, lattice parameter, volume fraction and the size. All these parameters will control the mechanism that govern the strengthening effect. So, as an example I can tell you, like a small lattice mismatch will create a coherent precipitate. What does it mean? That I may have a lattice and this is the lattice point, and here this is the solute atom which make a cluster to make a precipitate. Okay. So, this is almost like a coherent precipitate. Now, in such a case the local distortion depends on the extent of the mismatch. There is no doubt, because the lattice mismatch will create the lattice distortion. Now, coherent precipitate are capable of providing a significant strengthening effect, but precipitate with higher mismatch is less effective in strengthening, because then the dislocation will bypass and the strengthening can only be achieved by increasing the number of the precipitate, or let us say the volume fraction of the precipitate, when the precipitate has a higher mismatch. So, this is let us say an example of such kind of precipitation strengthening that we talked about. So, I show you another example in case of nickel aluminum, that if we need a nickel aluminum alloy to use for a higher temperature at relatively higher stress, let us say we fix here for 100 hours of life, then for a lower precipitation volume fraction we will get a lower strength. However, if we need to use for a higher temperature, then we have to go for a higher precipitate volume fraction. So, here is the situation where precipitate with higher mismatch will be less effective, and we can control that using the volume fraction of the precipitate. Now, if we have to go for a higher temperature, then again for higher stress application we have to go for higher fraction of the precipitate. Okay. So, this is the control that one should look for. Now, let us have a look at how to enhance the capability using some dispersion strengthening. So far we have talked about solid solution strengthening and the precipitation strengthening. Here, if we have a precipitation strengthened alloy, then we can raise the temperature to a single phase, we can dissolve it, or this is purposely dissolved in order to tune the microstructure, but it may also occur that I am using a edge hardenable alloy, this is called as precipitation strengthened or edge hardenable alloy at a higher temperature. During its service the precipitate may grow. Okay. In that case the strengthening mechanism will change and the service life will degrade or will lower down, okay, because the precipitate may also dissolve in the matrix at higher operating temperature. Okay. So, in order to prevent that, one of the alternative solution is the go for dispersion strengthening. So, here this dispersion strengthening is a particular terminology we use where we incorporate a second phase which is very small, but they are non-metallic. Okay. Non-metallic in bonding means in terms of they are oxide, nitride and ceramic particle. So, these precipitate they usually do not grow and the progressive coarsening will never be occurred in case of ceramic. So, here we employ a fine and uniform distribution of dispersoid particle that are essentially insoluble in the matrix. Okay. So, there are very nice example like we know aluminium alumina composite. So, I have a aluminium matrix, inside I have precipitate which are Al2O3 in a aluminium matrix. So, aluminium matrix has some grains and I may have inside this grain there are some alumina precipitate. So, alumina precipitate is ceramic in nature and they will not grow at all, okay, very less, the growth is very less, and they are also not soluble. Under such circumstance, we call it as a dispersion strengthened alloy. Another very nice example is the thoria dispersed nickel, TD nickel. Okay. The TD nickel has thoria particle in a nickel matrix. Okay. So, this dispersoid phase is not at all coherent, because they are ceramic and they have a very different crystal structure, lattice parameter than the matrix aluminum or nickel matrix. Okay. And it is not pronounced as precipitation hardening. In case of precipitation hardening, we can increase the strength to a very high extent, but it is maintained. The interesting point here, that we can allow this composite to be used at higher temperature, because the precipitates are very much, or dispersions are very much stable. Now, the other way of enhancing the capability is the controlling some grain size and grain boundary effect, because once we have talked about the second phase, because in terms of dispersion strengthening and solid solution strengthening, and let us say the precipitation hardening and so on. However, in a base alloy there are grains, right, and once these grains are exposed to higher temperature, the grain growth will occur, because the grain boundary will migrate, that is that will occur, yes, by diffusion. So, this grain boundary has a positive effect at lower temperature, because the grain boundary is strong at a temperature below the homologous temperature, okay, or equicohesive temperature. Equicohesive temperature means where the grain body and grain boundary, they have the same strength level. So, this is called as equicohesive temperature. Okay. So, this is usually at a 0.5 Tm is the melting temperature multiplied by 0.5. Okay. Now, the grain boundary are usually weak at a temperature above 0.5 Tm and very strong at a 0.5 Tm. It simply said that a finer microstructure will have a better strengthening effect at lower temperature, and a coarser microstructure has a positive effect as a high temperature material at higher temperature. Okay. And the reason is very clear, because we all know about Hall-Page equation. So, in a Hall-Page equation where sigma is basically is a proportional, where there is a constant into root d. Okay. So, here this is let us say a friction stress and dependent on the grain size, where k is the Hall-Page constant, right. So, in that case, if we can increase the population of the grain boundary or finer grain size, then ASTM grain size, this is as an example, then we can increase the strength much and much higher. ASTM grain size is larger grains, this is let us say ASTM 2, and the very finer grain is the ASTM 8 finer grain or ASTM 6. So, here we see that the proof stress at 575 degree centigrade, it is 752, whereas a finer grain size has a higher proof stress at this given temperature. That is good. However, you can see the major benefit that you can simply increase the fatigue life from 10 to the power 4 cycle to 3 into 10 to the power 3 times higher. A fatigue cycle can be achieved at a finer grain size. Okay. This is good. Now, at higher temperature, the grain boundary is the weaker region. So, what we can do? We can simply take this material and intentionally put some precipitate at the grain boundary. What it does? It simply impede the motion of the grain boundary. It will be stopped, because they are pinning the grain boundary. If grain boundary has to move, they have to move along with that. Okay. That will be a good purpose. How to do that? We can incorporate some carbide or boride particles by grain boundary engineering and incorporate those precipitate inside for a better creep resistance, as an example, UD mat is an example of such. So, here this is the base alloy with some zirconium and boron. In that case, the creep life can be increased such a high extent. You can see from 50 to 650 hour of use just by adding such kind of precipitate at the grain boundary, whereas the rupture ductility can also be improved. So, this is also another interesting or important way by controlling the grain size and introducing some grain boundary effect. Now, how to further improve that? Now, the second part I talked about, that was the creep, because creep is also important phenomena for designing a high temperature alloys. Now, here we will talk about different process in order to control the grain boundary population. How? We can cast an alloy by conventional casting method. Let us say super alloy we have cast using, or any alloy we can cast using a conventional casting. What it does? It will produce some equiax type of microstructure. Equiax microstructure, you know, like a honeycomb structures, and this equiax structure means the grain boundaries are quite large, and if we stress it such a material, then the cracks will appear at the grain boundary region. Okay. This is normal to the direction of the applied stress, that is expected. But if we go for directional solidification, means I have a large turbine blades and these are the grains due to directional solidification. This is a single grain, okay, you assume. So, this is a schematic microstructure is shown here. Okay. So, these are the grain, individual grains, and the grains are all aligned in a blade, okay, from the root to tip. This is, let us say, a root of the of a blade. This is from a root to the tip, and in that case there are no grain boundary that is normal to the measure applied. So, let us say the stress is applied along this way, and the creep life can be extended, because if crack has to appear, it has to appear here. Okay. The crack has to appear here. So, only in such a case the crack will appear, and the remaining grain boundaries have a very small element which are near normal to the applied stress and to initiate the crack. So, you can see that this is the creep strain and this is the creep time. Okay. So, in case of conventionally cast alloy, the performance is poor than the directionally solidified alloys. Okay. So, here we get a better service life. However, on the other case we can go for a single crystal casting, so or growth. So, in that case there are no grain boundary at all. So, the whole turbine blade is made out of a single crystal only. This is a single crystal, okay, using a seed crystal. We will go into detail of the processing of those alloys, do not worry. So, here there is no grain boundary at all. Okay. So, if we apply some stress, then crack will be very difficult and there will be no grain boundary. So, there is no grain boundary diffusion, only grain body diffusion, okay. That can be controlled by adding some rhenium and so on. Okay. So, this will be a very best material for a highest creep life. You can also see this is as a schematically I have shown you here, that you have a very large time compared to any directionally solidified or let us say conventionally cast alloys. Now, there are some other aspects like environmental resistance, which we partly talked about. However, for enhancing the capability, we can choose the alloying element. Let us have a look at some nickel based alloy. We want to add some chromium or aluminum. People have seen that there are some optimized condition whether you want a alumina on the surface after oxidation or chromia in the surface. Like in a stainless steel, you already know about chromia scale basically protect. Okay. So, this chromium concentration or aluminum concentration in a nickel based alloy could be adjusted to avoid some internal oxidation. Okay. So, alumina always provide a better protection during oxidation environment and chromia during contaminated environment in presence of some sort of sulfur containing compounds. Okay. So, let us say if we increase alumina content, then instead of forming nickel oxide we will get a mostly alumina oxide on the top, whereas if we increase chromium content we will get chromia, but there are some boundary and so on. So, the basic requirement is that we have an alloy and the oxide scale, this is an alloy and the oxide scale which one will dominate depend on the aluminum content or chromium content. This is interesting part. At the same time one can think that they should be sticking to the sample surface and provide a better protection, otherwise it does not make any sense. How to do that? The scale adherence is important, and we can adhere or we can make the adherence or improve the adherence by some sort of pinning effect. Okay. How it is that? In order to avoid spalling, we can use some active elements like cerium, lanthanum or yttrium. These elements form their oxides and these active metal peg the alloy at the oxide interface by some sort of mechanical keying effect and keep the oxide layer along with the base alloy, and that is one of the very beneficial effect of using any kind of any of these active elements like cerium and yttrium. Now, for ceramic for high temperature application, there are three important aspects that one should consider for enhancing the capability. One is the phase control, another one is the defect tolerance, another one is the thermal shock resistance. In that case, you have seen that ceramic may contain multi-phase and one of the phase is mostly like silica. So, this silica could be glassy or maybe crystalline. So, the strength basically depends on a certain temperature on the volume fraction of this silica, because if silica is in the glassy forms, then their strength would be different than the crystalline form. So, the amount of phases we can control for enhancing the capability for high temperature application. Now, since the defect tolerance is very less, in case of ceramic we have a very low fracture toughness or very less process zone size. So, during manufacturing process or shaping or any kind of other mechanical operation, the local stress distribution does not occur homogeneously, which will cause stress concentration in the material, and during its use the material fails. So, there must be a solution. How we do that? Like transformation toughening. There is a ceramic and we incorporate some phase which will transform and absorb the shock and absorb the stress. Now, the other point is the thermal shock resistance, means if we apply heat to a ceramic material, since the conductivity of ceramic is not so high as metal, there is a temperature gradient which will cause the material to fail. In such a case, the ceramic cannot redistribute the thermal stress during also plastic deformation and shock resistance. So, here it is an important criteria, people have find out that the temperature difference, that is delta T, like a shock resistance, how we can estimate that a given fracture stress of a material, the Poisson's ratio E is the Young's modulus and alpha is a coefficient of thermal expansion, will give you the how much thermal shock resistance a ceramic can provide. In such a case, I show you three different ceramic like alumina, silicon nitride or zirconia, or let us say lithium aluminum silicate, where the delta T for lithium aluminum silicate is the highest. Okay. So, by using some parameter we can estimate which material will provide us the better service life. So, with this today we finish our discussion, and we will continue other aspect of high temperature material in the next class. Thank you very much.